Okay. Actually, let's have example of utilize AI to optimize various stage of chiplet design. So we will start with the first thing, which is the lithographic hotspot detection. Actually, it's considered manufacturing procedure. So when we talk about new smartphones or smart devices in general, like iPhones, watch, laptop, all of these devices use modern chip with advanced technologies such as 5 nanometers or smaller in some cases. And these chiplets or chip, it can have billions of transistors in order to enable different features like AI acceleration, high performance game, multi-core computing, low power consumption, and more capabilities. But actually, when we talk about all of these features or these attributes in 5 nanometers, we could have something called feature shrink. The feature shrink can lead to a specific problem or significant problem, which is the manufacturing defect. Manufacturing defect, it's mean having a defect in the final stage of the product, and it will be very costly. So there are many methods have been proposed in order to overcome the defects in early stage or solve the defect in early stage before the manufacturing stage. The lithographic, actually, one of these methods has been proposed to find the defect in early stage. In the lithographic, actually, or lithography, actually, we try to create extremely tiny structure on the semiconductor wafer, or actually we can say it's like printing a specific pattern on the surface to define where the component of chips will go. For example, here in this image, we can see in the mask, we can have like specific patterns or layouts that we want to print on the wafer. So in some case, as a result of neighboring patterns or the feature shrinks, we could have like some of hotspot in the lithography. What we mean by hotspot, for example, if where we can see here on the black images, we can have bridging or branching. This kind of lithographic hotspot, it's considered undesirable patterns, and if we don't solve these patterns in early stage, it will be printed on the wafer, and then we will have like manufacturing defect. So we try to find this pattern in early stage. So we can have like a final note from here, like finding the hotspot in early design stage is mandatory to avoid any undesirable layout pattern in the manufacturing stage. So in the next slide, we will talk about using the convolutional neural network. As we said previously, it's considered suitable to deal with images. So in the convolutional neural network here, we try to have like these layouts or these patterns as an input for the model, and we try to have like a specific model or detection model to an image or specific layout is hotspot or not hotspot. Let's have zoom on how this model works. First, we will have like lithographic hotspot images, and these images will be changed to pixels, and these pixel will be moved to the model in order to extract the main features. Then build the deep learning model or convolutional neural network models, and then we will have a classifier model to classify if specific image is hotspot or not hotspot. So this is the model, and according to the result from the paper that proposed to using deep learning to solve this problem, they got this result actually according to the model accuracy to define whether an image it's hotspot or not, they got like around 100% or 99% of accuracy. And according to the laws of the model, it was like very close to the zero. And all of this during just 18 training rounds. And in general, we can say by applying AI in this problem, we can introduce an accurate, fast, cheaper, and reusable hotspot detection framework. So now we will use also deep learning in order to solve another problem. Here we will talk about BGAN. Here began consider optimization problem. We will talk about benchmark scarcity. First, when we talk about design a new EDA algorithm or design a new tools, we need to have like benchmarks in order to evaluate or validate the proposed method compared to the previous method. For example, when we talk about benchmark that can be used to test algorithm or test a new method to optimize power delivery network, we need to have benchmark to evaluate the new method. So actually the benchmark, it's like not something it can be easy to be available every time, because when we talk about benchmark for chiplet, we could have like obsolescence problem. What we mean by this, for example, when we have like a new design for chip with like less than 5 nanometer or with new materials, using a previous or old chip with another design or another material, it cannot be like valid to evaluate a new method. So we can't use only old benchmark to evaluate a new method. And also when we talk about new chiplet design or something like this, we could have like a confidential problem, because some companies, they can't sacrifice their data or like designs in order to have it like a benchmark. And also the design, it's like improved very quickly, and this makes it labor intensive to have all of these benchmark available. So here in this paper, they proposed to using GAN to generate realistic benchmark for BDA design in order to test and validate new methods. Actually, for the BDA benchmark, it's actually like a tool or method to evaluate the new design for AI drop and electromigration. In this paper, actually, they used the generative adversarial network to extract specific feature from the current map and train model in these features in order to generate a lot of new benchmarks that can be used to validate new methods. Actually, this paper based on the generative adversarial network that known as a GAN. And what we mean by GAN, actually GAN, it's like a deep neural network method that consists or contains three parts. The first part, it's the generator that's responsible to generate fake images or fake data. And that discriminator is like the another part of the GAN. It's responsible to distinguish between the images generated by generator. Are these images real images or fake images? All of these generator and discriminators based on the networks in order to train models to the generator to generate much better images, and for the discriminator to be much more better to distinguish between the images. Now let's see how GAN works in training. For the generator part, actually, it's started noise or like Latin vector generated by GAN, and this generated vector, it will give us like a noise images, and for the real images from the real data set, and the discriminator always try to distinguish between the real images and the fake images, and according to the discriminator performance, it can say this is real or fake images. Then we will have generator loss, and we will have also the discriminator loss. So in both of these laws, it will be fed again to the model in order to improve the capability of the generator and the discriminator. But actually, when we talk about GAN, we talk about model need a huge amount of data to be trained. But actually, according to this problem, we only have a few amount of benchmarks, and we can't provide the model with all the amount of data needed to train GAN. So in the next slide, we will see how we can have enough data to train GAN model. So due to we don't have like enough data to train GAN, we will use transformer learner to train GAN on source data, and then fine tuning the model on the target dataset. Let's see what we mean by this, because we have only few amount of data for the benchmarks. We will try to find some data can be very similar in the features on the current map data. Here, when we talk about current feature or the current map, we can find like here on this images, they try to find something similar. They used the satellite, urban satellite images generated by Google Map in order to use it as a source data set. They tried to do like some pre-processing in order to make it fit very well to the training. And in general, they had like 4,167 images. And according to the target data set, they only had like 10 current map or 10 real images that can be used in the fine-tuning stage. Let's see in the next slide how this has been doing. Actually, in the training stage, they started by the source dataset for the urban satellite images for the 4,000 images before that we had. Then they trained like GAN models. Then they moved the model through the transformer learner to the to fine tune it on the real images for 10 current maps, and this is gave us like a model or GAN model has been able to generate enough current map images to be used in the BDA. So in the next slide, we can say in yeah, this we can say by using GAN, we can overcome the data scarcity and the benchmark scarcity by generated enough images to train to train or to validate a new method. And also with the GAN, we don't need to train model on a lot of data. We can use transformer learning in order to solve this problem.